I decided to change my talk title because my title is New Approaches. But actually, I should say this is Old Approaches for quantum dynamics in condensed-phase molecular systems. So in my research group, we focus on various excited state phenomena in molecular systems. We study dynamics of Lie-Houston in Lie-Houston complexes and the various exciton or charge dynamics in molecular materials, and also spectroscopy modelings. In terms of in fields more related to quantum information processing, we are working on methods to characterize gate errors on IBM-Q and utilize those knowledge to implement gate sequences that would allow us to simulate, to utilize the noise on IBM-Q machines to simulate open system quantum dynamics. For example, we can simulate energy transfer dynamics and actually compare the results using intrinsic noise on IBM-Q machine and compare the results very nicely with HEOM numerically exact calculations. But today I'm going to tell you a story on how we do, we develop theories and pictures of theories to simulate condensed-phase quantum dynamics. So we have a genetic model for this. Basically, we consider molecules in a condensed-phase environment as two-level systems and with coupling between them. So we have a system Hamiltonian, electronic Hamiltonian, and we model the environment as a bunch of harmonic oscillators, and we have a bilinear system-based coupling here. The key parameters here are the electronic Hamiltonian, including psi transition energies and the coupling between those sites, and also spatial density, that's weighted density of states of the system-based interactions. And in our group, we can actually model this electronic Hamiltonian and also spatial density using either quantum chemistry calculations or molecular dynamic simulations to get those parameters. And with these parameters, we can actually employ some sort of a dynamical theory to calculate the full dynamics of such kind of systems, quantum systems. Now, there are a few general ways to treat systems like this. One is if you have lots of computational power, you can use like hierarchical equation of motion or QUAPI approach to calculate numerically exactly the dynamics in this kind of system. But they are often very time-consuming and only applicable for small systems. But you can also utilize perturbation theory. If you do perturbation based on the weak electronic coupling, normally it leads to Foster or Marcus type theory. If you perform perturbation based on weak system-based coupling, you have a Redfield type of theory. But those kind of perturbative theory, like Foster or Redfield theory, were not very successful compared to numerical exact results, especially in so-called intermediate coupling regime, where this electronic coupling and the system-based coupling are comparable in their amplitudes. So here we actually compare a Redfield approach with exact results. It's not very good. And also Foster and Redfield with these stats are HEOM results. So in our group, we developed theories to treat this problem. We want to treat large systems with hundreds of chorofields. So we developed perturbative theories instead of a numerical result theory. We have several different approaches. One is a small polaron quantum mechanics equation based on a polaronic picture of quantum dynamics. We also have a pure-dephasing reference system, or called coherent modified Redfield theory, that treats the pure dephasing of a system exactly. And more recently, we developed Schrödinger-Langevin equation approach that treats coupled vibration electronic dynamics exactly. So today I'm going to focus on these two approaches. And with this dynamical theory, we can use the obtained effective model Hamiltonian to calculate quantum dynamics and use the quantum dynamic simulation to calculate nonlinear spectral signals. This is very important because in complex systems, spectroscopy is the only way that we can compare our model with experiments. So let me talk about this pure dephasing reference system theory first. This basically treats to provide accurate quantum dynamics using second-order perturbation quantum mechanics equation. So the idea is this. Normally, we have a Hamiltonian, right? We write down Hamiltonian in a so-called psi basis, okay? And we can apply a unitary transformation to transform this psi basis Hamiltonian to another basis. If you transform this Hamiltonian to a diagonal electronic Hamiltonian, system Hamiltonian here, this is called acetone basis in the field, and this is so-called Redfield approach. But you can actually do the transformation partially. You can do this transformation in arbitrary, we call it the missing angle, and to get to a general basis. And this could be a so-called pure-dephasing reference system. I encode this missing angle as theta p here. So after this transformation, your system Hamiltonian is non-diagonal, so you have a coupling term here, which we can treat perturbation, perturbatively. You have this system-based Hamiltonian, which will be transformed to some mixed electronic state basis, and then you have a diagonal term here. The key idea in pure dephasing reference system approach is we treat this diagonal system-based coupling exactly. We include this diagonal coupling into the zeroth order Hamiltonian here and treat it exactly. And then this off-diagonal turn over the system-based coupling will be treated together with this electronic coupling using second-order quantum mechanics equation. But by this nature of our coupling includes this electronic coupling turn and this system-based coupling turn, this is basically leads to a Foster theory, and this leads to a so-called modified Redfield theory. By plugging this basically into the quantum mechanics equation approach, we automatically get a rate that actually is composed of three terms: a Foster term, modified Redfield term, and a closed term. So we developed a theory that very naturally interpolates between Foster and the Redfield theories. The next question is, how do we identify this good reference system, reference electronic system? We use a variational polaron approach to help us to find this. So this is a system in the psi basis, and we can actually apply a parameterized polaron transformation to transform this into a displaced basis. And we can then use this transformed Hamiltonian and based on Bogoliubov's free energy bound to find the variational parameter f. And this gives us some sort of reference missing angle at this optimized variational polaron ansat electronic states. And this is to show you that this missing angle actually depends on system-based coupling as various parameters. And in some parameters, you have this kind of unphysical abrupt change. And this is well known in polaron theory that is due to the insufficient size of the polaron ansat. If you increase the number of variational parameters, this will become smooth. Now, when we apply this theory to two-dimensional system with this kind of parameters, we found that our theory, this red curve, actually at a weak coupling, weak system-based coupling, it collide with the coherent Redfield theory very well. And at a strong coupling, it collides with Foster theory. And in between, actually works very well when compared to the exact QUAPI result in those black dots. So this theory works very well. Even in some intermediate regime dynamics where the both Foster and CMRT works not very well, our theory, this red curves here, agrees very well with numerical exact methods. So basically, this indicates a very important concept in treating quantum dynamics in condensed phase. That is, pure dephasing or dynamical energy fluctuation is key to correctly or accurately describe the dynamics. So I'll move on to the second topic here. And this is Schrödinger-Langevin equation approach. And this approach, we developed it because we want to treat strongly coupled vibrational electronic systems and calculate nonlinear spectroscopy. So we specifically want to calculate so-called two-dimensional spectroscopy. It's a four-way mixing technique. In this experiment, you pass 3 laser pulses into a system to interact with your sample and observe a signal coming from out from a phase matching direction and using a spectrometer to do a heterotime detection. So the sample generates some third-order polarization. And basically, you have 3 pulses, so you can control 2 time delays. The first time delay between first pulse and second pulse, we call coherence time, tau.